Hello guys, so today we'll be starting with the group B question, and here we'll be taking the question number 6, which is beginning with an empty binary search tree, construct binary search tree by inserting the values in the given order. After constructing a binary tree, you have to basically insert a new node, find number of nodes in the longest path from the root, find minimum data value found in the tree, change a tree so that the roles of the left and right pointers are swapped at every node. And fifth, search for a value. So yeah, let's just start with the binary search tree. So we will be starting out with understanding what is a BST. So BST is nothing but binary search tree. So before understanding binary search tree, we would need to understand what is tree. And before that, we would need to understand what's a graph. So let's start with a graph. Graph is nothing but a collection of nodes and edges. So nodes are represented as the circles and edges are nothing but the connection between these two nodes. So nodes may have some values and which is connected by one another using these edges. So this can be called as a graph. So a special case of graph where there is no cycle or no loop. So basically loop means if we start from any node, we move to another node, we move to another node, and we move to another node. And if we come to the same node again, this is called as a loop or cycle. So basically what we have to do here is tree is a special case of graph in which there is no cycle. So if we remove this edge, this is what you can call as tree. Why? Because here we have nodes, as in the graph, we have edges, but there is no cycle or no loop. So it is not connected. So this can be called as a tree, and we can also add many multiple nodes if we want. Okay. So if in this tree we add some constraints or rules, such as each node would only have two children. So let's say we remove this, so this, and yeah. So as we have added a constraint that each node would have at most two child. So here you can see we have two, here we can see we have one, and here we can see two. So a case or a tree in which each node has at most two childs is called as an binary tree. It is called as an binary tree. So what is BST then, or what is the difference? So basically, binary tree has a specific rule that each node would have two childs. But specifying a bit more, what does BST says is the left part of any or the left subtree of any node. So let's say this is our main node or any node, and the left subtree or the left part should always be smaller. So it should be smaller. So let me just write this smaller. And the right part should always be greater. So BST is a special kind of binary tree. BST is a special kind of a binary tree where the left subtree of any node is smaller than that value, smaller than that node, and right part of that node is greater than the node value. So considering an example, let's say I have uh, 5 at the node. So here this subtree should have less than the 5 value. So let's say 3. Here we can say 9. So here we can have again two childs. So here what can happen is uh, we will consider only this much part. We will consider only this much part. So this is again a node. So in this, it should have less value here and greater value here. So what we can do is we can add 2 here. 2 is less than 3, and here we can add 4. So what you can see is 2, 3, 4. This whole part is less than 5. And similarly here the 9, or we can add here 10, here we can add 15. So this whole part, the right part, is greater than 5. So basically, this is what an example of binary search tree looks like. So in this, for every node, for every node, the left part is smaller than that node value and right part is greater than that node value. So why is this needed, uh, or what is the special case, or how it helps? So let's say, uh, I assume you would be knowing I assume you would be knowing an algorithm called as binary search. So what happens here is, if you want to search any element, let's say I'm searching here 4. So what we can do in this tree is, we will start with 5. We will start with 5. Let me just change the color. So we will start with 5. If we know, we assume this is the made element, and we know that if we are finding for 4, it should be less than. So we can directly ignore this right part, as we know uh, the right part would always be greater. So we can directly skip this thing and we can move to this part. Again, at the center, we have an element. We'll again check left or right. It will give us right, and then we will again check and we will get the element. Or else we may not get it also. Let's say we have some value as 4.5. So here both of the childs are empty, so we won't get. But this returns the value in log n complexity, and the storage is also efficient. So yeah, this is the main benefit of an binary search tree. So it is easier to search in this tree and find out or retrieve the values easily. So this is how the basic things work. So let's just start with few terminologies in the tree, which we would be looking further. Okay, so the first element or the topmost element is called as the root element or the root node. Then, assuming any node, let's say I assume 9, so I can call this as node. Okay, it would have children. So the node connected to it in its below level. So we can call this as individual levels. This is level 0, level 1, level 2, level 3. So these are all levels. We can call this as levels. So level 0, level 1, level 2, and level 3. So something like that. So whichever node is present in the next level and connected to the current node is called as children or the child. So it is the child node of this 9. And assuming this as a child node, it will call the above as parent node. It will call it as parent node. Then assuming this node, it has two children, 2 and 4, and we can call this as siblings. So something similar to what we draw in our family tree. So I would assume we have always I assume everyone has drawn some family tree. So we start with grandfather and grandmother, then uh, your mother or father, similarly grandpa and grandma, and your mom. Then they both you. So something like this. You can draw a whole tree. Similarly, here, if you have multiple childs, you are siblings. You are called the child, and they are called the parents. And yeah, so basic terminologies in trees too. So yep. So let's say we will be starting with some random numbers as given in the questions. You would be given as a list of numbers. So let's just start with some random numbers: 5, 9, 8, 15, 2, and 3. Okay. So we will be given these numbers. We have to start from an empty binary search tree and create a tree out of it. So yeah, let's just start. So we will be taking out first element 5, and here as starting we don't have anything, so we will directly add 5 as a root. As we don't have anything, we'll start with the 5 as a root. Let me make this a bit smaller. Okay, yeah. So starting with 5. Then let's move on to the next element, 9. So here we know 9 is greater than 5. So what we have to do is we have to put this 9 to the right of the 5. Okay, done. Then we got 8. Now I again know it is greater than 5. So what I will do is I will first check with 5. So it is greater than 5, go to right. Then there is a node there. So I will again check, is it greater than 9? No, it is less than 9. So it should be on the left of the 9. So here binary search tree follows how right part is greater than, so 9 and 8 is greater than 5. Yes. For 9, left part is smaller. Yes, 8 is smaller. Okay, let's move further. 15. So 15 is greater than 5. We go to next node. So 9, it is also greater than that. So here we get 15. Then for 2, 2 is less than 5. So we go to the left. Then for 3, it is less than 5. Okay, less greater than 2. Okay, so it would come here. So this would be the binary search tree for the given data. 5, 5, then 9, 8, 15, 2, and 3. So this is how we have to do it. Let's break this a bit. So here I can see we have some node which points to left and right, and it has some data. So what I can do is, let's assume I create an class. Let's say I create a class with node which has data, left pointer and right pointer. Okay, so we can assure that there could be only two children's, left or right, as we are talking about binary search tree, and there would be a type of data. So I could create a class like this. Okay, node, data, left and right. Okay, this would be this nodes, and then okay. So a basic in general algorithm I can write down is check all node, check node until you don't find any empty space, until you don't find empty space. So basically we have two condition. If it is greater, if value, the value which we are going to add is greater than current, so we will go to right part, else we will go to the left part. Okay, simple as that. And yeah, so what we are doing is we would first check for 5, then for 9, then for 15, and then do the thing. So as we just said, check until you don't find empty space or empty node, empty position, and if value is greater, put it in right. If value is lesser, put it in left. So we have to do this basic thing. So let's just try to program this a bit. Let's say I have the same array. Let me just take this. We'll use this a bit. Okay, let me paste this at center. So we'll be starting. So I just mentioned we'll be using node which would have data left and right. Sorry for the bad handwriting, but try to understand. Then we would need to create a binary search tree. Let's say that is also in class binary search tree. Okay, so start and end. So constructor, we will start with an empty node. So let's say this dot root equal to null. Okay, why? Because currently we don't have anything. Then we have to insert value. You would get a value. Okay, so what you have to do now? So in the insert value, what you will be doing? You will first of all checking if this dot root equal to null or not. So if it is null, we will add a new node at this root. So this dot root equal to, let's say, new node with the value whichever we want to give. So let's say instead of value I write v for simplification. So this becomes our base case, that if there is no root, what we have to do. So let me just reduce this a bit so you could see everything. And yeah, so this happened. Now what we have to do is, so if root is not empty, if the root is not empty, you have to check, or what we can do is, there are two methods now. Either you can go iterative method, or either you can go recursive method. So how you can see this? You would ask how you can say this is whether there is an iterative and recursive. So most of the recursive code can be converted into iterative and vice versa. So it can be done. In trees, we mostly use recursive. Why? Because it is easy to implement and it doesn't take a much of efforts or much line of code. So it is easy because, let's say this is the case. Okay. If this is the case, if we are starting from here, what we can say this is, if I erase these things and say I will be starting with here. So this is the same thing as starting with the above node. So basically the same things are repeating itself. So we mostly use these recursive things. So here also we can use recursive. So what we will do is, so here we directly added this dot root to the new node. We would have to make few changes if we need to make this recursive, as we would need the root where we are going to add this. So basically, again rewriting these. So let's just copy uh, below. Let me paste this. Okay. So here. Okay. So now what we'll be doing is, let's try to think what we can do. So as I said, recursive would need an extra node and all. So let's first try to think if iterative simple or not. So what I have to do is, until and unless I don't get a blank spot where I can add, I have to go on finding that blank space. So what I could do is, I could try a while loop and set it to true until and unless I don't get, or I don't break out. So what I can do is, before that, if you have to traverse on the route, you would need some temporary variable so that you don't lose your direction to the route. So let's say I take an current which is equal to the route current variable. This would be of type node. Okay, let's just keep those node and means details. So while true, what I will do is, if value is greater than current dot data, current is a node. So if it is greater than current dot data, what we will do is, we need to move to the right side of this node. So this is a node, current is a node. So I need to move to the right side. So what I will do is, I will update current to current dot right. But here there is a catch. Let's say I have something like 3, 2, 5. Let's say here 4. Okay. So I am here. I want to add 6. I go to the current dot right. I come here. I now want to go to the right. As I am adding 6, I want to go here. But this is pointing to null. So there is nothing. So this would then lose, which basically if I need to add here the value, I need the reference to this 5. But here I'm directly shifting or changing. So what I need to do is, before moving further, I need to check whether current.write is empty or not. If it is empty, as like in this case, if it is empty, I need to add to the write. So if current.write is null or empty, if it is empty, I need to add here. Okay, add node. Else, so here we need to else. If I add node, I need to break here. This is becoming a bit messy. So yeah, okay. Change the color. Okay. So if current.write is empty, means before moving, I would check if it is empty. If it is empty, I will add the node and break out from the while loop. So basically, I have added the element, or I could directly return. Else, I need to move to the next current. So basically, if I am here, I would check if 6 is greater than 3. Yes, it is greater. So what I need to do is I need to go to current.write, as it is not null. So as current.write is not empty or not null, I move further. So current is equal to current.write. Again, when I check, again it is greater. That time I have to check if current.write is empty. Yes, I can see here it is null. Then I could directly add a node here as 6. So I'm basically doing this. Okay, let's just try implementing this in code. You would get a more better idea. So let me just save this file. So yes, let's add the basic code template. Okay, so as mentioned, we need to create a class node. So I will create a class node where we will have this dot okay, int data equal to, let's say 0, and then I would have a node pointer left which will be pointing to null, and then a node pointer right which will be also pointing, okay, null should be written like this. Okay, so this would be our basic node. What I could do is, then I need to create a class bst. Okay, binary search tree. Let's say construct. Okay, the constructor here I would set this dot root equal to, let's say null. This won't have anything. So yep, so starting from this, okay, I would need to define root. It would also be a node pointer root which would be pointing to null, or we can directly do this too, instead of constructor. Okay, I would need an insert thing. It would take a value, so let's say it would be an integer value, or you can directly pass the node itself, but I assume I will be creating that. So let me just create that. Node temp equal to new node and the value. Okay, first the new node, then temp dot data equal to the value. If you need to pass the value here itself, you need to create a constructor here. So either ways you could do as you want. Then, so let's just try creating this. So bst uh, tree, let's say t. Okay, yeah. So let's execute this. And executing, we got an error. Request for member data and temp. Okay, yeah. So here, temp is a node pointer. It is not a node itself. So I can't use dot notation. I need to use arrow notation. So, yep, execute. Okay, yeah, this is private. Data is private. I need to create this public. So, yes, let me just do some indentation. Here also, let me create these things as public. Okay, let me execute. Where did it- Yeah, after class, we need to give a semicolon. I always forget to do this. Yes, so it finished successfully. Means it compiled successfully. There are no errors. So now, uh, yes. So what do we need to do now? If, as we said, this root, so this is also a pointer to the class. So if this dot root equal to null, so if it is null, what do we need to do is we need to you pass the root node, pass the new value to the root itself. So I can do like this. So this dot root will be directly pointing to the temporary node which we just created. Else, else like we just saw, we can use a while loop. So while true. So what do you need to do here? We will basically check the value and the node value. So before that, as we just mentioned, we need a pointer, current pointer, which would be pointing to the current node. So this dot root. Okay. So what we'll be doing is if value is greater than current dot data. So if the value is greater than current dot data and if current dot write equal to null. So if it is equal to null, we will add. So current dot write equal to, okay, current is an pointer. So we would need arrow notation. So current dot write equal to the temp, the new node which we created. Else, okay, we need to break then. So break. Else, what we have to do is we can use a else statement, or we know if this occurs, it will break. So we can directly write here also. So what we need to do, if this is not the case, if it is not null, we need to move to the right. So current equal to current dot right. Similarly, if this is not okay, if this is not the case, if the value is not greater, so it will be less than. So it may be less than or equal to. So we assume a hypothetical condition that we will not get equal values. We will get unique values every time. Or if you also consider that you would be repeating the values, the repeated values will get added to the left part of the tree. So it would be left biased. So it depends on how you implement. So my tree would be left biased. So here, else if we know the value would be less than or equal to. So if current of left would be equal to null, then we will be adding to the left. We'll be adding the temp to the left and break. Else current equal to current of left. So we will move to the left node. So yep, this is how it would work. And okay, let's try executing this. So after creating t dot insert, let's say 1. So executed. Okay. So it was the root condition. So it executed well. And let's give this as 10, the root node as 10. Insert 1, then 15 greater, and then 3. Let's execute this, and everything went well. So how would we know everything went well and left and right are correctly assigned and correctly done? So we need to traverse to the tree and see whether it worked correct or not. So what we could do is we need to traverse the tree. So let's get back to how we can do that. So here, assuming this tree itself, what we will do is we will try to iterate, or we will try to move through all the elements in this tree. Okay, so what I could do is I could go to each node in fashion as root. First I will go to the root, then I will go to the left, and then I will go to the rightmost part. So if I follow this format, and if I search, I could get some kind of a representation, or I could traverse all the elements in the tree. So this is basically a traversal method. So this is called as pre-order. Okay, so as you can see, root is present before the left and right node, so it is called as pre-order. Then we have something as in order, which is similar to this, just uh, it is a bit different at here. So root is at the middle. So yeah, just a second. Yes. So first we will travel left, then we will travel right. Sorry, first left, then root, then right. So it is called as in order. And then we have something called as post order. So in this, route will be traversed at the last. So yeah, route is traversed at the last. First left, then right, then route. Okay, so post order. As you can see, pre means at first, so route is at first. In order means in middle. Uh, you can see here route is in middle. Post means after. So route. So this is how we can traverse to the tree. So you can easily implement any of this thing, but we'll be going with the in order. So why in order? Let me again consider a tree. Let's say 3, 9, 2, then I need to enter 1, so I will enter 1, then 8 and 15. Okay, assuming this tree, what would happen in order? Okay, so let's try performing in order. So in order says first go to the left, then root, then come to the right. Okay, as you say. So I will start with this node. I'm saying go to the left and then come to the root. Okay, I go to the left. So I'm at this root, and I again say I'm at this node. I again say I need to see the leftmost thing. So I go to here. So I got the left. So I try to go again to the left, but there is nothing. So then I come back to the root. So I print 1. Then I try to go to the right. There is nothing. So I come back here, and so the left part of this node is complete. Okay, so left part of this node is complete. So I will go back to the root. So yes, I go back to the root. So I will print root, then go to the right part, but there is no right. So I again come back. I then print the root, then I go to the right value. So here again, this is the same tree. This can be considered as an individual tree. So what I will do is in this root, I need to go to the leftmost value. So I will go to here, there is nothing. So I come back. So 8 will be printed. Then right, there is nothing. Come back, 9 will be printed. Then go to the right, 10 will be printed. If you see here the values 1, 2, 3, 8, 9, 10. It is following some order. It is sorted. So this is the feature of the binary search tree. If you use in order in the binary search tree, you get a sorted list, sorted value. So basically we don't need to check whether left is correct, right is correct, this and that. We can directly use the in order and we would get sorted values. And we could then confirm that our BST is working fine. You could try this for any tree, and for every tree you would get an sorted value if you perform the BST correctly. So let's get back to our code. So here let's implement an in order. So before that, uh, yeah, okay, here we are returning nothing. We need to specify void. Then how did this work? Sorry, execution. It is working fine. So let's try printing, then we would get whether it is correctly working or not. So again void in order. So yeah, so this would basically start with the root node and work. So what I would do is in order will take a node. Okay, node pointer node. Here also insert int value. Okay, works fine. Here it will take the node and we will implement this recursively, as recursive is easy. So what we will do is we will check whether the root is null or not. If it is null, we will just return. If node equal to null, just return back. If not, then what we have to do is you have to go to the leftmost thing. So you have to call the in order for the left part of this node. So node dot left. Okay. While going after going to the leftmost part, then what you will do is you will print the root node or the current node which you got. So cout, let's say okay, yeah, node dot not dot node arrow data. Similarly here also not dot node arrow left. Okay, I will print the node. I will then give a space. Then I will again call in order for the node right part of the node. So this would be the basic function for searching. Let's just try executing this. If this works, I will explain this again. Executed this, and yep. So it is assuming an argument, but I haven't provided this. So what I can do is I could say I could give a default parameter as this dot root. If you got nothing, consider this dot root. So if I execute it now, okay, let me just check. Okay, dot maybe. Let me just execute this once. Okay, now call to void node uses default argument for parameter 1, which is not yet defined. Maybe this confuses it. I'm not sure what happened here. Let me just provide it t dot root. Okay, this would also give the same value. So yes, 1, 3, 10, and 15. Okay, I'm getting this as sorted order. So it makes sense. The BST is working correct. So let me again add these things and see what happens. Okay, I again got the sorted order, means the BST is working perfectly fine. So let's go back to our question and see what all steps we completed. So we started with an empty binary search tree. We constructed a binary search tree by inserting the value in the order given. Okay, that is done. Uh, after constructing a binary tree, insert a new node. That is also done. Find number of node in longest path. Okay, this is not done. Find minimum data, not done. Change the tree, okay, not done. Search a value, okay, this is near about done. Let's get back to the code and see. Okay, here you could see you are printing each value. So instead of printing, what you can do is you can just see whether the node data value is equal to the data which you're finding. So instead of verbally explaining, let me just use this. Okay, so let's return a boolean whether it is present or not. It would ask search to take a node, let's say a value, int value, and a node pointer which would be used for traversing. So if node equal to null, return. And here in the cout we will use if the node's data is similar to the value which we are looking, will return true, or else after doing everything, if we don't have anything, we'll return false. After performing in order, checking and in order for right, if we found nothing, at last we'll return false. Here also, if node is null, so here also we will return, let's say, false. Okay. Yeah, let us try. So cout, we have to print to see whether it, okay. Let's make this understandable too, the in order thing. Okay, let me comment out, execute. Okay, in order, correct. Now I need to search. This should be t dot search. T dot search for 3, let's say, and end line. Execute. Okay, it expected 2 things, so I will give this dot root, not this, t dot root. Okay, so search. Why is it again printing all the thing? If return true, else return false. Okay, clear. Okay. Okay, it is calling for in order. Here you can see search is calling for in order. So if in order is called, it will perform the printing. We need to perform search here. CARCH. Copy paste things just went wrong. Okay, executing. Okay, here you need to pass the value to value and the node. So value and the node, execute. Okay, false. What did we give? 3. Okay. Okay, so here we need to, okay, so yeah, the issue here is if we start here, we get a return value, means the search may return a true or may return a false. So if any of this search returns true, we have to return true. If this returns true, or if any of this search returns true, because we are going into depth. So if those return true, we have to return true, or else we have to return false. So here, let me store this in some variable. Let's say answer, bool answer equal mm, equal to, let's say, false. Okay. So here answer, or let's do a or, means if this returns true, the answer will be changed to true. And yes, here also let's do the same, answer or equal, and here also answer or equal. Why? Because we are not sure whether we go. Okay. Here we can directly return, as we know it would be true. But here we are not sure, so we will be returning the answer. So if search returns false, false or false gives us false, false or true. Let's say answer is false and this is true. So it would return true. Let's try this, and yes, you can see 1 is printing. 1 means basically true. So true means 3 is present. Let's say 11. 11 would not be present, and here you are getting 0 means it is not present. So search is done. So moving forward, we had one question that we have to find the minimum value. If we get back to the understanding, or we get back to the tree here, you would see we said that whenever we would be working with the in order, whenever we working with the in order, we'll get an sorted order. Okay, sorted means the minimum element would be at the first. Minimum element would be at the first. So which was the first element we printed? So if we see correctly, we started with the root, we moved to left, 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 and the leftmost value or the leftmost node would give me the least or the minimum value. Similarly, if we go to the right, 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 and the rightmost value would give us the maximum. How and why? So let's get back a bit and go to any of the tree. Okay, assuming this tree. Okay, so what we are saying is we are on this node, we need a minimum value. We know minimum would be in the left part. Okay, move to the left part. Here we got another node, we know it would be in the left part. So if there is nothing on the left part, so what we can say is the node which we are currently on is the minimum. Why? Because whenever we move to the left, we are finding the value which is less than the current node. So here it is 5, 2 is less than that. If here it would be 1, then 1 is less than 2, then only the 1 will come here. So basically minimum values are the leftmost value. Similarly, on the same logic, if I need to find an maximum value, so it should be greater than 5, so I move to right. It would be greater than 9 also, so moving to the right. Again I move to the right, and the rightmost value would be the maximum. Why? Because we have generated a tree such that every rightmost value, every right subtree or the right node value would be greater than the current. So moving further and further to the right, we get the maximum value at the end. So similarly, for finding min and max, we would have to just do a simple thing. So getting back to the code here, uh, here we would return int, and our function name would be min. It would take a node, and we will try to implement this uh, recursive only. So let's just copy this in order. Or okay, we can go iterative also, or recursive is fine. Okay, if uh, node dot left. Okay, we just said if there is nothing on the left means it is the last value. So what we can say is if node dot left equal to null, then return node dot data. Return node data. Else what you should do? Call the min again and pass the node of left. If node of left is null, we would return the node data. If not, then we will go and find the minimum. So let's execute this too. Let me just copy paste, reduce the terminal size a bit, and paste. Instead of t.search, t.min. and I need a root. Okay, I will pass the root, and yes, let's execute. Here you got 1 because 1 is the minimum. Let's say I add -1 and I would get -1 as the minimum. So similarly, I could just create a max function too. Instead of min, I create max. Instead of left, I just need to go to the right, and this would give me the value. Copy, paste, instead of min, max. Execute, and we got 15. So this is how we can search, we can print, we can first of all create an insert node, then print the whole tree, then search for it, find min and max, and yes. So this is so now let's just find out the maximum length or maximum nodes in a path as given in the question. So we have to find maximum number of nodes which are in any path. So what we can do is uh, let's move back here, and here if we start from any of the node, uh, if we start from the root of the node, what we can say is we need whenever we move to the next layer or we move to the left or right or any of the child. Let's say I store a value of height equal to 0. So this is 0th value. Whenever I go to the left child, I increase it by 1. Then if I again go to its child, I will increase it by 1, and I will go on doing the same thing. And whenever and for each step, if the height value is greater than some threshold or greater than the maximum value, let's say I will store some max value, and if it is greater than that, I will just store it. So it's simple as that. Go to each node whenever you're going to its child, just add 1, and that's how you can find the maximum number of node in the path, any path. Okay, so we would basically, let's just copy this in order because we have to traverse the whole tree and calculate. So instead of in order, let's rename it to calculate height. Let's use camel case, and yeah. So I would get a node. Each node I will check if it is okay. I have to return a value. So instead of void, I will return int. And if it is null, I will return 0, means there is no height. What I will do is whenever I calculate the height, so I would, let's show I have a value max. Okay, how to set that value max. So let's say I have an int value max which is set to 0, and what I will basically do is max is equal to maximum of the current max value and the value I got from 1 plus the calculate height for the left node. So what I'm basically doing is I'm calculating max between the current value and the 1 plus height. So the height of the tree from the node of left. Similarly, I will do here also. We don't need to print. Okay, sorry, I just got confused. So what you have to do is you have to basically find the max from either the left subtree or right subtree. So what you have to do is you, instead of doing this, so what you're doing is you're checking max and then 1 plus height of node of left, and here it should be right. But instead of this, what you have to check is whether there is a longest path on left side or whether there is a longest path on right side. So you have to compare between those. So what you have to do here is you have to take max 1 plus calculate height from node plus left, sorry, node of left, and 1 plus why 1 plus, because the current node is also considered in that. So 1 plus calculate height in the node of right. Okay, so this would give us the max value, and instead of putting, let's just return this. So whenever it would go to the leaf node, it would return 0. Whenever above that, +1, and +1. Like this, we will get in the calculate height. So let us print this too. Instead of max, calculate height, execute. Okay, H should be capital, execute. Okay, there is some max. Okay, max is not defined. So for using the max function, we would need to include an header file called algorithm. Let's execute this. Okay, here there is an issue. Uh, Basically, we are calling a max function which is inbuilt, and we have already defined a max function here. So instead of max, let's give max value, and here also use camel case. Similarly, here instead of min, let's use min value. Similarly, here also min value and max value. Now it should work. Okay, you can see it is working, and the maximum value is 5. So you would ask how 5? So we would need to create a tree out of this so that you understand. So let's copy this, move to the so let's generate a tree from this. Okay, so considering 10, so we have to first add 10. So 10 would be here, -1, it would be here. Okay, -1 here. 15, it would be here. 3, it is greater than -1. Less than 10, greater than -1. Then 10, again 10. So we just said it would be left biased. So 10 is less than 10 is equal to 10, so it would come here. 10 is greater than -1, so it would come here. It is greater than 3, so 10 here. Then 1, so 10 is 1 is less than 10, so it will come here. It is greater than -1, yes. Less than 3, so it would come here. Then 15 again, so it would be left. First of all, it is greater than 10, come here. Then it would be left biased, so it will come here. Why? Because if it is less than, we will add to left. Then again 3, so it will check for 10. It will go to the left. It will check here. So 3 is greater than -1. Then it would come to here. 3 is equal to 3, so it will be left biased, so it will come here and greater than 3. So here, if we just check the height, so this is 1, 2, 3, 4, and 5. So maximum value is 1 here, here, here. So this is how the maximum height gives us 5. And yeah, so this is how we can calculate the height. And the last thing is to swap each of the nodes. So what I can do is I could create a void swap tree. So it would be a swap tree function. This would take a node as normal. So what we have to do is we have to swap each of the node. So we have to swap each of the left and right child. If we go back to the question, you can see here, change a tree so that the roles of left and right pointers are swapped at every node. So you have to basically swap the right and left pointer to at the every node. So what I could do is uh, we could just the base case that the node, if node is equal to null, then we would just return, we would do nothing. But if it is not null, what we have to do is we have to go to the left of the node. We have to go to the leaf node. So basically calling the swap tree, swap tree for the node of left, for all the left nodes, and the swap tree for all of the right nodes. Okay, we went for all of the left and right nodes. Here, after going to all of the left nodes, so basically going to the left, uh, whenever you are returning, what you have to do is you have to basically, what you can say is, whenever you're returning, you just need to swap the left and right node. So what I could do is I could create a temporary node pointer, let's say temporary, and assign the right pointer to it. And then node of right would be equal to node of left. Okay. Then node of left would be equal to the temp. So basically swapping the right and left. So using the right, storing it in the temp, then putting the left in the right, then putting the right in the left. So this is how we could work. Let's just try swapping this and see whether it works or not. So it doesn't return anything, so we need to directly call this for the t.root, and let's just call the in order again. I think we would get a difference in the in order. So yes, so here we swapped each of the node, and here what we get is in order. Let's just verify whether this is correct or not. So assuming the same tree, what we are doing is we're basically going to the each of the node and reversing it. So what would this give is, let me just select this first all, reduce a bit, okay. Reduce a bit, copy paste, and here, okay. So, okay, instead of copy paste, let's just build it. So 10 would be here itself, 10 would be here. What would basically happen is we will start with here, we'll go to the left, then there is no left, so here we will be swapping, and basically what would happen is 15 would come here, right, 15, then -1 would here, 3 here, 1 here, and again 3 here. So something like this will happen, swapping each of the element. So in order would give me something like uh, 15, then 15, then 10, then the left 3, then the right again 3, then 1, then -1. Okay. Yes, 15, 15, 10. Okay, this gives an uh, descending order or sorted elements in descending order, not in the ascending. So this is how we can swap. So that was all about binary search tree, I think, because we covered all of the questions mentioned in the question 6. So let's again go through it. So insert a new node, done. Find the number of nodes in longest path, done. Minimum data value found in tree, done. We also did maximum. Then we changed the left and right. We searched. We printed the in order. Yes, so all of them are done. Basically, we completed this whole question, binary search tree. If you have any doubts, you can put those in comment section below, or you can join our communities and put your doubts there. And yeah, this was all about this video. Let's just meet in a new video.